recording. Yay, so today we'll hopefully finish AR. I didn't expect to spend so much time on AR, but there are so many interesting topics within it, it's hard to not go over things. Very quickly, I'm going to write up the final project requirements and also add the parts of A9 and A10 for people who need to do those to make up points. I was originally going to have a real-time demo session, but that's going to be a disaster given all of the questionable internet connections like my own, where it just drops every like 15 minutes or so. So I'm not going to do that. Instead, what you'll do is like serious game style, where you just record and do a voiceover of what you were doing, your findings, and so on. And during the finals period, I'll just play these videos, sort of how the serious games final works. And if possible, still join it because there are lots of cool projects and you can ask questions about how people did things and stuff like that. Just be supportive. I mean, it's the last day of finals, so unless, like, some people have an actual final conflict, in which case it's fine, but most people's finals are done at that point and you don't have anywhere else to go, so try to join if possible, even just to listen in. You still have a report. It'll be 2 pages of actual text with normal margins. Some people used margins that were like 1.5 inches for the midterm proposal. The font size will be 11 points, which is standard for the SIGGRAPH format, and it'll be single-spaced. So your text by itself should be 2 pages of the SIGGRAPH template. Even if you do it in Google Docs, like, it should be obvious if you actually met the requirement. Like, if you were to paste this into the SIGGRAPH template, the normal one, not the horribly screwed margins one, like, it should actually make up 2 pages. You should be able to eyeball it. 2 pages in Google Docs, where it's single column format, would probably actually be longer than the SIGGRAPH template. But in any case, just like, don't try to fill it with images. You can have images as long as you meet the text requirement, especially if they clear up your explanation. Don't break up each question into a section. A lot of people did that. The problem with the 2 pages of text requirement is that section headers in LaTeX are really space consuming. So don't do that. Just make it like a normal format, like intro and things like that. I'll write this up, but just write it as if it's a normal final project assessment or review or whatever you were doing. And then we'll finish up AR. So we'll talk about SLAM, iterative closest point, how you actually do AR in game engines, and then holograms. So last time, you can look at the old lectures, but last time we were talking about some reconstruction methods, how depth sensors work, some different reconstruction methods like computationally, or the geometric methods, or sometimes they're called physically based methods or analytical methods. Most of these are based on this idea of Delaunay triangulation, where you basically create a bunch of points that have a uniform. Actually, I don't remember exactly how. Well, my explanation is not going to be totally accurate, but you try to create a bunch of points. Well, you draw lines between points that meet certain requirements, such as a certain distance away from each other. If you were to draw a circle around each point, it shouldn't encompass another triangle. Things like that. From this, you can also get a Voronoi diagram, which are these diagrams where you're drawing lines that are like an equal distance away from the points and things like that. It's not worth going into detail because you won't do that in this class. And there are a lot of algorithms that do this automatically, but there are some cool ideas if you're into the math part of it. We saw some methods. Ball pivoting is the most common method for geometric reconstruction. Then there are these iterative methods such as Poisson surface reconstruction, which try to find a radial basis function or a moving least squares function, which are interpolants like splines, except they're functions that are trying to wrap around, or just like it's like a 3D way of fitting a function to a bunch of points, which you've probably done before with lines and things like that. This is just more complicated and with surfaces, but it's an idea that you're probably familiar with. So we talk about some hard reconstruction cases like thin surfaces, reflective surfaces, various types of interference, and there are recent methods like one that came from UNC a couple of months ago that can do things like thin surfaces and reflective surfaces pretty well. Perfectly reflective surfaces like mirrors can't be done well at all because there's no way to reconstruct them. but you can use them to reconstruct other parts of the room, which is cool. But anyway, moving on, where we stopped was photogrammetry, that high resolution. Photogrammetry is, those of you in the computer vision class probably already know what it is or have heard of it, but photogrammetry is basically you take a ton of images from different viewpoints and you use some computer vision techniques to infer the position of the camera at any of these points. Like for example, if you take a picture of this house with your phone from all these different angles, your phone is not tracked, but you can sort of figure out where it is relative to another image using basic computer vision. You can find features that are consistent and use some iterative methods to figure out like which feature is which. Like if you want to align the corner of this house, for example, here it's actually kind of a hard case because it's symmetric, but in any case, you're trying to align features between images and then you're converting them into 3D with epipolar lines, which if you're in the computer vision class you're familiar with. It's not worth going into detail because this is just almost a purely computer vision topic, but the idea of epipolar lines is from some feature, you can figure out based on where that feature is in the image, where the camera is, and you can do that for multiple cameras, which it creates basically two edges of a triangle, and the third edge is found by drawing a line between the two cameras, and from there you can triangulate the point. But epipolar geometry is not in the scope of this class. There are some deep learning methods which will help you figure out the object of interest. So if you have a much more complicated scene and you only want to reconstruct one part of it, you can use a method like YOLO. There was some example here about why is it doing that? Some example here about doing this for like really large scales. Like in this case, they reconstructed this huge part of a city using just a bunch of satellite images and probably some images from like planes or helicopters or something. But this is how Google Earth works basically. Like in Google Earth, you can zoom in and see buildings, and some of that is inferred by building measurements, like there are databases of how tall buildings should be. But in a lot of cases, you can just do it with images because satellites are basically taking tons of images and rotating around the Earth, so they get a lot of views of the same object. Anyway, moving on, there is this other, like you can do photogrammetry in a game engine, and it's often used to construct really complicated assets like nature, or like things in nature like rocks and trees and things like that. So you can see these assets are really high quality, and they have nice textures and shapes, and this would be pretty hard to do from hand. So people just do it with photogrammetry. They take a ton of pictures of these objects in real life, then use some photogrammetry solver that finds the 3D mesh, and then you can put it in your game. And things in nature are especially important they're an especially important application of photogrammetry because it's really hard to reconstruct things in nature well by hand because it's a little bit hard to infer like what looks right. A lot of that is not super intuitive. Like we as humans just see that things look or don't look right. Like for example, you've probably seen this example before where like humans look really weird if you make them perfectly symmetric, but it's hard to explain why. Natural objects have sort of the same problem. It's just an uncanny valley thing. Like you can tell if something looks or doesn't look right. I'm not going to show this, but there was this good talk by the people by Epic Games about how to make content using photogrammetry. I thought it was a really good lecture, so you're free to check it out if you like this kind of thing. So anyway, moving on to AR again. We want to measure pose over time because AR devices like the Hololens and the Oculus Quest and so on are basically moving depth sensors. And so we need to figure out where these depth sensors are moving so that we can get an accurate reconstruction of the thing that we're looking at, or at least we can get an accurate pose in 6 degrees of freedom relative to the real world for AR so that we can align objects correctly. And so how do we know where these devices are between frames? And I put inside out tracked because that's important. if you're tracking things externally, like with the Vive, which has IR sensors that are little blocks that are at the corners of your room, you don't really need to use image-based methods because if you have external trackers, you can easily triangulate where the rays are intersecting and things like that. And there are wave-based methods. But with these inside-out track devices like AR devices, the Oculus Quest and things like that, you don't have external trackers, so they need to infer their own pose based on these cameras that are tracking outwards. So anyway, how do we know where they are based on the information that they have? And how do we know that some object that we're looking at, a 3D object that we have reconstructed, like a table or another person or something, is the same in one frame as it was in another? Like, let's say, for example, in AR, you want to add more monitors to your desk, but they're virtual monitors. And let's say that you want those to always stay in the same place in the real world. We need methods that tell us that that actually is the same place in the real world as it is in the virtual world. And the methods that we use to do this are ICP and SLAM, which help us localize these objects and figure out which object is which using point clouds. So iterative closest point is a really important method in reconstruction. It was proposed in 1991, and it makes the assumption that at least some of the points in your point cloud between two frames will be pretty close. I guess, I don't know if I think I mentioned this before, maybe briefly, but a problem with point clouds is that between frames, you don't know that the features that are in one frame are going to be in another frame because there's some randomness associated. Like maybe your computer vision algorithm doesn't realize that, like maybe your iterative method doesn't realize that this one feature, like the edge of that house, is the same between frames. It's just, there's a lot of randomness with iterative methods, so you can't assume that your point cloud will have the same points between frames, like they're not going to be aligned already. Look at this butterfly, for example. There are a bunch of extra points in the blue butterfly that the red butterfly doesn't have. Also, points in a point cloud, like when they're saved to a PLY file, are not ordered, which is a whole different problem. So anyway, to deal with these problems, we use iterative closest point, which makes this assumption that a lot of the points will be probably close to other points. They might not be the exact point, but you can at least converge onto some alignment. And in dense point clouds, this is a totally fine assumption. So what iterative closest point does is it keeps making guesses about how to align the points, and it uses basically mean squared error to figure out if the alignment is good. And with that, it like pushes the meshes in a couple of different directions, and it applies some rotations, and with each time step it applies a very small transform and then figures out, like, did that transform bring me closer to an alignment or farther, and it uses that to do the next time step. This is exactly how gradient descent works, except this is just with a bunch of random points. So it's basically trying to minimize the mean squared error between 2 point clouds. And there are some more complicated ICP type methods that use curvature, but we won't discuss those. Those are very complicated and their performance is actually not particularly great. But anyway, iterative closest point is important for any, like if literally anything in your setup is dynamic, you need to use ICP. Whether it's the depth sensor itself that's moving, like in AR, the subject that you're trying to reconstruct is moving, like we saw markerless tracking methods before where they were trying to reconstruct moving people. ICP is needed for any of these methods because any kind of basically anytime anything moves, you're going to have a completely different point cloud. So you need the ICP to figure out which point cloud is which and where it corresponds and how do you align them and things like that. So this is an important concept in any kind of 3D tracking system that is dynamic. You don't have to worry about static camera pose and subject because in those cases you can just use computer vision or photogrammetry. ICP does converge pretty quickly, but it becomes a problem where the number of points that you have will accelerate the amount of time that it takes to find a convergence, like a good alignment. So you can do it stochastic style where you just take some subset of the points There are other methods that do it locally. The stochastic method is not great because the features are not ordered the same between the point clouds. Like, you don't know that the points are the same, and you don't know what kind of correspondence there is, and there's just a lot of randomness with point clouds, so it's not always a good idea to just throw a bunch of points away. What's more commonly done is you handle the features locally. So for example, maybe you draw a voxel around this part of the butterfly, or this butterfly is 2D, so you can just draw a square, and you try to find points in this butterfly that correspond to this part. You can do that with almost anything that is not symmetric, and most real objects are not symmetric, so that's fine. So local point alignment's more common and more stable. There's this good video on iterative closest point that you can check out. I think he does a pretty good explanation. He's not the most excitable person ever, but he does a pretty good job of explaining how it works, and there are some examples here. So you can see that they have some initial, well, say that this is one point cloud and this is another. It keeps pushing one of them to the other so that they will eventually align as best as possible. So if you understand gradient descent, this should be like pretty intuitive. So you see that this is happening, and I can't share audio, but this guy makes he makes a really useful point, which is that in this case they're trying to reconstruct the room from a robot's perspective, and they actually use the IMU to say that to realize that, like, the robot only rotated in yaw, like its head only moved up and down or something like that. So that gives you a lot of information about where to rotate the point cloud so that it's aligned, because if only one dimension moves, you only need to predict one dimension basically, and maybe some translation. So you can make assumptions like that based on the tracking system to make ICP converge faster. Here's the other ICP, Iterative Clown Posse. Really solid videos if you want to lose brain cells. So before we move on to the next topic, you might have not seen this in a very long time, but you might recall the Euler method for making predictions about differential equations, like basically trying to match or trying to predict what one function or what a function will look like, or yeah, I guess that's what it's for. I don't remember, it's been a long time since I've taken this class, but the basic idea of the Euler method is you take the current position that you're at, you use the derivative at this time step, so how fast the function is changing, to predict the next step, and you have a time parameter which basically tells you how much should you move. So with gradient descent, for example, you can choose how wide each of these iterations is. So that's the Euler method, and there's a reason that I'm asking you to recall it, which we'll see in a second, but the idea to remember is that the predicted function, which in this case is the red one, its shape is pretty close to the true function, but it strays more and more as you keep making predictions, because it's essentially just adding a bunch of local predictions together. I hope my recording didn't break. No, it didn't. OBS Studio just turned black for a second. I was worried. So the reason I bring this up is to talk about the next topic, which is related to IMUs. IMUs do this basically. IMUs just record a bunch of deltas. So if you don't have any kind of global correction, and you just add a bunch of deltas together, you'll get this error accumulation. And SLAM sort of tries to mitigate this a little bit by aligning things and localizing them better. So SLAM is a bunch of methods that try to figure out where the device has moved between two frames using some feature that it found in an image. This is the localization step. And then it saves whatever reference point it used to figure out or to slowly reconstruct the scene and get a mapping between its own movement and what the scene actually looks like. Here's a good video that shows more or less how it works. So you have this robot that just has a couple of cameras and it's using a feature from the camera view to figure out where the environment is, and it uses that to slowly reconstruct the environment. And there is some inaccuracy, which is what ICP would be used for, like trying to align the two different views. But you can see that this really simple robot can figure out what the environment looks like pretty quickly. And in this case, I think they were tracking the blue tape specifically, but you can track other things. Mute yourself, please. So anyway, you can see the effect of what SLAM is trying to do. You can find papers on SLAM. I mean, it's a really common method. It's probably, in many ways, it's almost fundamental in robotics. So you can find plenty, god damn it, you can find plenty of resources on how it works. And it works pretty well by itself, but the problem is that if you have multiple instances of your simulation, like this robot simulation, like for example, you have a HoloLens and you turn it on and off, how do you know that the part of the room that you're looking at in the second instance is the same as the one that you were looking at before? Like for example, how do you know that you're in the same room? How do you use pre-computed rooms? Like for example, let's say you have a pre-computed reconstruction of the room that you're in. How do you know to use that one in your current simulation so that you can save resources? And there are a lot of problems related to different instances. Another example would be like, how do you know if a 3D object that you have reconstructed before is the same as one that is in your real scene? So for example, how do you know that the person's desk is that desk and not just some other desk? You can use a method like ICP to figure out the context. Without ICP, these SLAM methods typically use dead reckoning to figure out where the environment is. So for anything that's not externally tracked, like a lot of AR headsets that don't have any external trackers, like the HoloLens, for example, and a lot of robots, what they do is they use dead reckoning to make a prediction about how much the robot has moved or the headset has moved. Dead reckoning is basically the Euler method that we just saw, where you're using the previous position plus the time that actually elapsed times a factor plus maybe like how much you know it has moved or accelerated, or there are a lot of different ways to do it, but it is basically the Euler method where you're making some prediction based on the delta, and then you can use ICP or just image-based tracking to make various corrections, which gets into what Micah has been asking a few times already about, which is the Kalman filter. But that's actually the next slide. But in any case, the important thing to know is that SLAM is used by pretty much any standard 2D or 3D track device. It's a really common method, and you will see it anywhere, pretty much everywhere if you're doing anything in robotics or in AR or VR. So Micah has asked a couple of times about the Kalman filter. So for people who don't know what that is, I might as well mention what that is. The Kalman filters assume that you have one sort of accurate sensor that's doing dead reckoning, like an IMU, something that's recording only deltas, which you are adding to your previous prediction over and over again, basically how the Euler method works. And then you have some other, probably inaccurate sensor that's doing a global estimate of where you are. So, for example, a GPS or images or depth sensors. We saw a couple of lectures ago the paper by Foxlin where they had IMUs attached to the feet, and they were using the GPS they were trying to accurately track this person as they were walking through a city, so they used the GPS to find a rough estimate of where the person was, and then they used dead reckoning to find a really accurate prediction. But what Kalman filters do is they dynamically compute things like the covariance, the error, what corrections you should make to make the prediction better, and things like that, to try to reduce drift. And they're really good at that. But the problem is that IMUs don't have a global estimate if you're not using any kind of inside-out or external tracking method. So if you're not using cameras, if you're only relying on internal sensors, you only have deltas. You don't have a global estimate to use to correct the accumulation of error. So that's... Mute yourself. I'm going to mute you then. Anyway, so filters in this case won't work that well. What they can do is they can reduce local errors, but for a single sensing unit like an IMU, which only relies on deltas, you can't solve the global errors that come with that. So for example, if you are relying only on IMU data and you have a one-off error like a sudden discontinuity, like there's some interference or you drop it or something like that, and that causes like a huge spike in error, the Kalman filter is good at dealing with that. And other filters are also good with that. But this won't solve drift or error accumulation without a camera. So if you do have a camera like an RGB or an RGB depth camera, your image basically is the global estimate. And with that, you can use the Kalman filter. And I think it's the next slide, but I actually looked into the Oculus API, and they do use a Kalman filter for this exact reason, to try to correct the Oculus Quest tracking. Some limitations of this particular filter: if you have sensors that can't really estimate their own error, or they're really finicky, like really cheap sensors have this problem, then it won't really work that well. The Kalman filter in particular assumes a Gaussian covariance, which in many cases isn't true. There's this other filter that's similar called the particle filter, which is good for this kind of situation. I think they're slower, and I don't know that much about particle filters. I think they're slower and harder to compute or something like that. But anyway, if you have a lot of interference, you won't have a Gaussian covariance because there are a lot of things that could be causing error. From what I know, the Kalman filter requires a decent number of time steps before it knows how to make the correction, which could be a problem, especially if you have something like interference, which is causing sudden discontinuities. So there is a little bit of delay. In VR, it's actually not a problem because you can't see the real world, but in AR, it is a bit of a problem. So for the Oculus Quest and the Rift S and these other inside-out track devices, you can check out Facebook's own information about how they did this. They have this tracking system called Oculus Insight, which is really interesting. But what they do is they find a couple of good 3D features in the physical environment, which they use to track the device over time. And they use a Kalman filter with that as the global descriptor, basically. You could also probably do it with a 360 image and figure out like how much your current 360 image differs from, I don't know, maybe the 360 image that was generated when you first did the Guardian calibration. There are a few ways you could do it, but it seems like the way that they described it, they use only a couple of 3D features. Like, for example, if in my situation, my tracking space would be like my fridge or my desk or something like that, a mini fridge. For a device, thanks Google for nothing. For a device like the HoloLens or Magic Leap, your global estimate is usually a very low poly version of your reconstructed room, and there are these things called spatial anchors, which we'll see in a second. So we've seen a few times now these analytical and iterative methods, so I just wanted to summarize the importance of knowing both versions. We've seen these in a few different contexts. For example, in IK, we've seen some geometric and analytical methods of finding angles. For example, the law of cosines is just a geometric method. But then you have other iterative methods like Fabric, which start from the previous pose, and then they keep pushing the previous pose towards the goal pose until you have a good current pose that tries to reach the goal as best as possible while also being continuous. This is an iterative method. In reconstruction, we have these physically based and computational geometry methods like Delaunay triangulation and Voronoi decomposition, which they compute edges based on just geometric assumptions about the points, and they use like circumcircles and things like that. Then you also have this implicit function that we've talked about, where you're iteratively trying to find the parameters of some nth order function that's a certain amount of complexity that describes the surface. This is an iterative method. It's very hard to geometrically figure out the implicit functions, especially if there's a lot of noise. In tracking, we've seen analytical methods like the Euler method and dead reckoning, but you also have iterative methods like ICP and SLAM, which iterate and try to figure out, how do you align the two point clouds. But you can get some assistance from the analytical method by using IMU data and things like that. which give you a rough estimate of how far those point clouds should be from each other based on like how much you've rotated or translated. So these analytical or geometric or physically based methods that we've seen are really good for handling things that we know or constraints that are really well defined. The iterative methods are really good for handling things that have noise, or if you have a free or a bound variable. Like in IK, there's almost always some rotation that you don't know for sure. You have a range of rotation that's possible, but you don't know the exact one. In 3D graphics, in almost every context, we'll use a combination of them. Those tend to be the most stable solutions that you'll find in papers, because we have a lot of sources of noise and unknowns, but in 3D graphics, we have a lot of constraints that are easy to handle because we have only a certain number of dimensions, which isn't necessarily true in machine learning. We also have some just really intuitive constraints like how far a bone can rotate. And we also have a lot of closed surfaces, like human meshes will probably be closed. So you can use both analytical and iterative methods in conjunction and get really good solutions that you'll see in some of the papers if you decide to go through the resources. So for point cloud processing, there are some good options that are open source, like MeshLab, PCO, which is just point cloud library, and Blender. MeshLab is really good at the mesh processing part specifically. It's way better than Blender at doing things like this. Blender can handle point clouds, but it won't do it very quickly. MeshLab can import a point cloud that's millions of vertices almost instantaneously, whereas Blender would struggle with that. MeshLab's not really good at doing anything more than that, which is kind of why it's just called MeshLab. So you can't do modeling or animation, but for the mesh processing part, it's really good at that. PCL it doesn't have an interface as far as I know. It's used as a programming tool, like it's a library that you can import to Python. It's huge, and it has a lot of good, it has plenty of good resources, and it's easy to find example code, but there's a little bit more legwork to get things actually working correctly. So in a context like if you're trying to do mesh processing with Python, PCL is better. If you want to do automation, for example, if you want to process hundreds of point clouds the same way, you would need a bash script to do this in MeshLab. So this is a quick comparison of these programs that are meant to handle this. In VR, you can still do reconstruction, and there are still really important uses of reconstruction, such as avatar reconstruction, tracking people's faces, which we've seen before. And there's this other interesting paper that you can check out from 2016 on using the real environment to reconstruct, or you reconstruct part of the real environment and then create a virtual environment out of it. It's a really cool idea. So this was the mouth tracking paper that you've seen before. We've seen it multiple times, where they have cameras under the Oculus that they're using to track the mouth. Then there's this other paper, which this image came from, where they are trying to they reconstruct the real world, and then they use that to procedurally generate a virtual world, which is a really cool idea. And then you can walk physically around this virtual world that was reconstructed. And you can use real walking, which, as we know, is a really good locomotion method. This is definitely a mixed reality application, where there's not really much ambiguity if it's MR or VR. It's definitely MR. So how does an AR character work, like in a game engine, like if you were to implement this? AR devices rarely have controllers, like the HoloLens only has like a little click controller, but this is starting to change, like the Magic Leap has a tracked controller. The HoloLens 2 will do hand tracking, and it might have a track controller. But the AR character is still structured pretty similarly to a VR character. So in most cases, you'll have your tracking route, and as we'll see in a second, the tracking route in AR is a little bit different. And the child of the tracking route is the headset, the controllers, your hands, and other devices. So this is the case in the Oculus Quest, probably the HoloLens 2, although I haven't gotten my hands on it, things like that. This is just a standard way of doing it. When the controllers or the hands are relative to the headset, so for example, I believe the Vive Pro's beta hand tracking works this way, and also the Leap North Star works this way. The controllers or your hands are a child of the headset itself, not the tracking route. And if you don't have any controllers at all, then you just have the tracking route and the child is the headset. In many cases, with the HoloLens 1, I believe the world origin of the virtual environment is aligned to be the starting position of your AR game. It's not important, it's a very minor detail, but in any case, you just have a tracking root and a headset, and all of your inputs are handled with gestures. So the structure is still pretty similar to the VR character. In AR, your tracking root is usually your initial head position projected down to the floor. So headsets like the HoloLens and Magic Leap already know where the room mesh is because they reconstructed it, so they already account for your height automatically, and so they just use X and Y in Unreal or X and Z in Unity, and they just shift the entire virtual world to your position. So it's sort of the opposite of VR. In VR, you are basically you're basically moved to the position of your character and where they start out in the virtual world. But in AR, what happens is that the virtual environment it's more like it's shifted towards your position in the real room with some head offset or with some height offset. But it's still pretty similar one way or another, which is the important part. There's a lot of overlap between AR and VR in terms of the programming. The locomotion, thankfully, is less important because you can just physically walk around. So I'll briefly talk about these important features of AR APIs. In the HoloLens, you have spatial understanding or spatial awareness, and then you also have a separate API for spatial anchors. The Magic Leap calls them spatial mapping or persistent. Well, it calls spatial understanding and awareness spatial mapping, and anchors are called persistent coordinate frames. In any case, this first term is used to describe the library that aligns the physical and virtual world. It basically wraps the SLAM and ICP features. It has a bunch of nice features, like it can give you the mesh of the real room, which you can use for collision detection. So, for example, in your game, if you were to throw something, or if you were to shoot a gun, and you want the bullet to stop at your wall, the spatial awareness or the spatial understanding library already handles things like this, because it will just give you the mesh and it will also generate the collision. So that's pretty nice. Like it already does the mesh collider stuff automatically, which is convenient because that's a pain. It also has some other built-in functions for like ray casting, like in the HoloLens, if you tap, it will shoot a ray towards the real wall or the real mesh, so you can select them, which is pretty cool. Spatial anchors they basically define those 3D features that you use to do the 6 degree of freedom tracking. So, for example, like I mentioned before, the Oculus Quest uses only a couple of features from your 3D environment to figure out where it is. Those are basically spatial anchors, although the Oculus doesn't call them that, the HoloLens does. And this is done automatically anyway in the HoloLens and Magic Leap to try to stabilize your holograms, so when you place things in the real world. But you can also define them manually, which is handy. I'll show you a couple examples of why it's handy. Well, one example that I don't have much experience with is these spatial anchors were intended so that you could share spatial anchors between different AR devices like the HoloLens and Magic Leap, and this spatial anchor defines the same 6 degree of freedom position or transform in the real world, so that you can align virtual items inside of both devices, which is a pretty cool multi-user application. It's not seen very often outside of advertisements, but it's still a really cool idea. I think one of the reasons why this isn't done that often is because it's kind of a pain to get working. For my purposes, what I use it for is you can define some plane that you tell the API to try to align yourself or try to do the best tracking within this range, or when the user is looking in this particular direction. And this is really good if you expect the user to stay in one place for most of the time. So this is the function if you ever want to implement this in the HoloLens. It's pretty easy to use. But an example is for our surgery work that we're doing at UNC, we expect the user to be looking at the apparatus that they're doing the surgery on. So the fake body or the training apparatus or whatever. So we would use a spatial anchor to tell the HoloLens to do the best tracking when they're looking in that direction. And this is nice because it will help avoid jitter when you're looking in that direction, which is a really important application for us because we're tracking really small objects. And if there's a little bit of jitter that misaligns the real and virtual objects, it's really noticeable for small objects because that tiny amount of error basically gets multiplied when you're looking at a tiny object because you only have so many pixels as a reference point. So just to briefly go over how do you actually get these devices to work. With the HoloLens, there was a partnership between Microsoft and Unity that resulted in the Unity integration for the HoloLens being much stronger than in Unreal. For example, the Unreal can't actually build for the HoloLens 1. It can stream to it, but it can't build for it. The streaming is still kind of handy. Like I've used it for Unreal's good UI elements. Like Unreal has an interactable web browser, which is cool. And the animation system, as we know, is better, at least in my experience. It's a little bit hard to get Unity's working. Thankfully, you don't see that much animation yet in AR, but still, it's good to know that you can stream and use different options if you need to. Unity's HoloLens integration is called Mixed Reality Toolkit. It used to be called Holo Toolkit, but when the Windows mixed reality devices came out, even though they're not really mixed reality except for the tracking, when these came out, Microsoft's goal was to share the API between them, which is always nice. The OS that it uses is called, well, the API, OS is not really the right term, but the API that it uses, like its platform, is called Windows Unity Platform, or sorry, Universal Windows Platform. It basically is Unity Windows Platform, being that the HoloLens only really works in Unity, but in any case, UWP is basically a better version of Windows RT, which you might have remembered being a hot thing when Windows 8 came out. Windows RT was like the tablet version of Windows 8. Most of UWP is embedded inside of the Windows 10 SDK. And I already mentioned streaming, but you can stream the images from Unity or Unreal directly to the device so that you can avoid having to build. This has similar benefits of using the Oculus Link versus doing it side quest style or trying to, build the APK and then push it to the Oculus Quest with ADB. It's just a pain. So the streaming has a similar benefit. It makes development way faster. You can't do certain things, like you can't use the HoloLens's camera while you're in this mode, at least as far as I can tell. So that kind of sucks, but still, it makes development a lot easier that you can even do the streaming. Some features of the HoloLens's API, or at least getting API features to work. In Unity, there is this, I actually had Unity open. In Unity, you have to set player settings, like you have to go into project settings, player, and then there are these capabilities, and you basically check the capabilities that you want. Like spatial perception is it's the spatial understanding library, spatial awareness, whatever you want to call it. There are things like webcam and microphone, and internet client and internet server. You need to check these in Unity to get them to work correctly in the HoloLens. Otherwise, the HoloLens just won't let you do anything. So this is pretty important. Like if you don't have spatial perception enabled, what it will do is it won't show anything in Unity in 3D. It'll show you basically a little AR screen that is playing your Unity game, almost as if you were playing it on a monitor that was virtual. It's really weird, but it's pretty useless. Thanks, Google. So in Unreal, you don't need to do this, but Unreal can't build for the HoloLens 1 anyway, so it doesn't really matter. But for the HoloLens 2, as far as I can tell, you don't have to do this. This thing called Windows Device Portal is used to manage your apps and file system on the HoloLens. The build process is awful. You have to switch to UWP in Unity, which those of you who are using Unity know takes forever. In Unreal, thankfully this is trivial. In Unreal, you just kind of check boxes to make things cross-compatible. But since Unreal can't build for the HoloLens 1 anyway, it doesn't matter. Anyway, once you build in Unity, this will create some Visual Studio project in some directory. It doesn't create the packaged application, like it doesn't create the APK, although the HoloLens doesn't use an APK, but in any case, it doesn't build that. It builds another project, which you have to build again. You need to open this in Visual Studio, then configure the project correctly, and then play it on the device, or at least tell Visual Studio to play it on the device, and then you have to wait for it to build again, and hope that the HoloLens doesn't go to sleep while it takes forever to build. So really fun. Not the most developer-friendly process ever. For the Magic Leap, it's basically the same, except for the Magic Leap, to get anything to work at all, you need to register as a developer and add your application and get all this stuff working. It's a pain. The API is still basically the same as the HoloLens, except it also has an image tracker, which it's a little bit questionable, but it's cool if they have it. It also has an eye tracking API, which will give you where the eye is focusing as some 3D position. Their sample applications are not great at all, and they're not really good at all at explaining how to do anything useful with eye tracking features. So that's not fun. Whereas the mixed reality toolkit for the HoloLens has a ton of samples. The OS that the Magic Leap uses is called Lumen, which is a variant of Android. What this means is that, well, we'll see why it's a good thing, but what this means is that there's not really any simple cross-compatibility with any VR device. Like the HoloLens can easily just you can push code onto mixed reality devices and it'll still kind of work. That's not the case for the Magic Leap because this is an OS that's not really compatible with anything else. The Magic Leap is x64, which means that you can do a couple of interesting things related to multi-threading, and the rendering tends to be better. In my experience, the colors tend to be nicer, but since we don't have a physical device, it's hard for me to make any good comparison that will make sense to you. It also has streaming capabilities. Its API features are basically the same, and to enable them, you still have to do the capability stuff in Unity. And unlike the HoloLens, Unreal actually can build projects for the Magic Leap, and the setup process is basically the same as the Quests because they're both basically Android devices. The Magic Leap has this thing called Magic Leap Device Bridge, which is basically the same as ADB for Android. So it's some command prompt feature that you use, or some shell feature that you use to manage the device, push applications, things like that. It does make the build process a lot easier because Unity will build this thing called an MPK, which is like the Magic Leap version of an APK, and then you just use Magic Leap Device Bridge to push it onto the device. So it's just a simple command as opposed to trying to build it again. You don't have these annoying cache problems that the HoloLens has where the Visual Studio project that it builds sometimes doesn't update correctly, especially if you have Visual Studio open while you're trying to build it. So there are just a lot of annoyances with the HoloLens build process that don't exist with the Magic Leap, so that's nice. We don't actually have that much time left, which is sad, because I thought the next part was cool, but we have Monday. As for Vuforia, I want to mention briefly because if you want to get marker tracking working really easily, I do still think Vuforia is the easiest to get working, even though it's proprietary, which is sad. Their sample applications are really great and it's very easy to get working. So the Unity store already has a bunch of Vuforia stuff, so it already has, get this out of the way. It already has like its basic samples, but it also has Magic Leap specific samples. It has a HoloLens integration somewhere. Here it is. And things like that, which have a lot of good sample code, which is nice and easy to get working. And these are already pre-configured to work with these devices, which is nice. It takes very little effort to get them working because they already have sample apps, which also work with these own APIs sample applications, which is nice. To get Vuforia working, you still have to register as a developer, kind of like with the Magic Leap. Then you create a project and it will give you some API key, which you'll then throw into Unity. Like it'll be here. And if you don't have this API key, then it just won't do anything. Then you can register the images you want to use inside of Vuforia's developer portal. I might as well show, since we can't finish the rest of the lecture anyway, I might as well just finish on this slide and show you what the image targets look like. So you have a license manager where you register your projects. You have a target manager where you actually register your markers. So I have a ton of these markers and you upload them, like you can add target and it'll ask you for the image, how big you expect it to be, what its name is. You can add some other types of targets like models, and then it will add them and it will tell you like how well it expects them to track. Like for me, the dragon tends to be really easy. It tracks really well for some reason. Here you can see the features that it uses. So that's how Vuforia's website works. Yeah, you give it the image, the expected size, the expected size will pretty much just be its real world size, because in Unity and Unreal, in AR, the virtual and physical environment are aligned, so the virtual size will be the same as the physical size. OpenCV, I mentioned OpenCV before, but it's not easy to get working with these devices. The Unity integration for OpenCV is not great. Unreal's is still pretty good. There's this project called Augmented Unreality that you can check out if you want to use that. This whole situation is caused directly by the fact that OpenCV was meant to be used with C++, which is Unreal's programming language. The basic OpenCV Unity integration is paid. It has a lot of useful sample projects, but it is paid. Like, it's $45 on sale, I think, and $90 not on sale. It's definitely harder to get working with these devices, and part of it is that the camera can be hard to interface with. Like, it can be hard to get the images to send correctly from the Hololens to these APIs. And OpenCV has much higher required specs, so that can limit its accuracy by quite a bit. And because OpenCV relies so heavily on the calibration being good, this is just a huge problem in general. Vuforia tends to be really good at inferring these things, and it works with low specs, so most people prefer it. Just an example, well, I already showed you this, but in the story you'll get this. I'll go over other types of VR displays and holograms next time because we don't have time, so you are free to leave. Bye.